Welcome to the next lecture on digital communication. So today we will be discussing about uh, multivariable or multivariate distributions. So what I mean is in last lecture we studied about a single random variable. So we had a random variable x, okay, and if it were discrete, then you know that it was characterized by probability mass function. That is, we asked a question: what is the probability that this random variable x, capital X, may take some particular value small x, and this was denoted by px of x. Okay, and in case of continuous as well as discrete, we could not ask this question in continuous, so we can ask that what is the probability that this random variable x takes value up to small x, and this was denoted as fx of x and was called as cumulative distribution function. Okay, and also for continuous distributions we defined probability density function, which appear to be the derivative of CDF. Okay, now in this lecture we will try to study that what if instead of one random variable we have two random variables, suppose x and y, and in general these two random variables may depend on each other. Okay, depend on each other. So dependency here means that if x takes some value, it has some effect on y. So when x takes some particular value, y cannot take value independently. Now, to give the example of what it means, so here is one example. Okay, suppose you have two coins in your pocket, and coin number one is fair coin. By fair coin I mean that probability of head is same as probability of tail is half, and coin number 2 is unfair. Okay, it has been manufactured in a way, the weight and the density of the material in the coin is put in such a way that suppose there is more chance of getting head. Suppose probability of head is 3 by 4 and probability of tail is 1 by 4. Quite possible. Okay, now let's represent with x, which coin you choose. Okay, so if you choose first coin, this x takes value 1. If you choose the second coin, x takes value 2. And for timing, let's assume that the probability of picking up any coin is half. Okay, so you can say that probability of this x is equal to I is half for I is equal to 1 2. Now let y denote the outcome of coin toss. Okay, so here is the experiment which you will perform. You will first pick a coin and toss. Okay, I will not go into detail of this experiment. It is very interesting with respect to the concepts of probability. The only thing I will try to emphasize here is that suppose if x is 1, that is you have coin number 1. Now y can be 0 or 1. So 0 means suppose head, 1 means tail. But the probabilities with which these 0 and 1 appear, they are different now. Because suppose x is equal to 1 means it is a fair coin. Now if x is equal to 2, that is you pick up unfair coin, again y can be 0 or 1, but now y is equal to 0 has more probability. So here x and y, they depend on each other. So the what value y will show, it depends upon what value x has already shown. This is one example where x and y are not independent, they are dependent. Okay, we will try to give a notion of it. Now let's come back to general structure. So if you have a joint random variable, we call them joint random variables. We can define joint cumulative sorry okay cumulative distribution function. Okay, so what is that? So when you had a single random variable, you would ask a question: what is the probability that x is less than or equal to small x? Now you put a comma here. Comma, as I told last lecture, I think that comma means and y is less than or equal to y. Now when you ask this question jointly, this is defined as notation wise f x y small x small y, and it's called joint cumulative distribution function. Okay, and see, in this way this joint cumulative distribution function fxy is valid for both discrete as well as continuous. Okay, now for discrete in particular, suppose you have a discrete pair of random variables x and y, which in general may depend on each other. So you can ask this question. In single random variable case, for discrete, you would ask a question: what is the probability that random variable x takes some particular value small x, right? Now here, in case of joint random variables, you can ask simultaneously and y is equal to small y. I again emphasize that whenever we use comma in probabilities, it has a meaning of and. So this can be denoted as pxy of xy, and it will be called joint probability mass function. Of course, it is valid only for discrete. Okay, now what can we do in case of continuous? So you have a continuous pair of random variables, right? So if you remember, in case of discrete, you would do what? You would differentiate this with respect to x, and you will get the PDF, probability density function. Now we have here two random variables. So what will you rather do is, so you have now a joint PDF. So you differentiate it first partially with respect to x, okay, then take a second derivative with respect to partially with y, right? So then this will become joint PDF, probability density function of xy. Okay, and if you remember, when you had a single random variable and it should satisfy the property, one of the important properties, normalization property, that if you integrate it from minus infinity to plus infinity, this should sum up to 1, right? Now here you have one more random variable, so you had to put double integral now. Okay, that should be equal to 1. And the other property is obvious, that PDF probabilities can never be negative, so PDF has to be non-negative. Okay, so this is about joint random variables. Now here one important notion we will introduce is about independence. Okay, so before independence I would like to give a notion of conditional probability. And I think the example which we again I will repeat that example which I quoted in the beginning of lecture, that we have two coins. Okay, one is fair and one is unfair, and the random variable x denotes which coin is chosen. 1 means fair, 2 means unfair, and y is then when we toss that coin, whichever coin we pick up, it shows head or tail with different probabilities. Now if you look at it, we can ask this question, that what is the probability that coin shows head given, so here is the language I'm using, given fair coin is chosen, right? And actually the answer, it should be half, right? Because you are choosing a fair coin. But other question is, suppose what is the probability that coin shows tail given unfair coin is chosen, that's coin number 2. Although answer of this also, it is 1 by 4. Just recall that example. Now how to put it in the notation? So the notation is like this. So we write probability. Now coin shows head, suppose the first part. Head means x is equal to, sorry, coin shows head, I'm sorry, I had to write y is equal to, suppose 0 means head, given the fair coin was chosen, so the given is denoted by this bar. Fair coin is chosen means x is equal to 1, right? Similarly, what is the probability that coin shows tail, that is y is equal to 1, given unfair coin is chosen, x is equal to 1. Okay, so these are called conditional probabilities. Okay, conditional probabilities. And here is how they are defined. So let me start with, if xy is discrete and its joint probability mass function is pxy x comma y, okay, and marginal probability mass functions. What is marginal? Marginal means we are given a joint random variables, but if we talk of x only, so if we forget y, suppose, what is the probability mass function of x? That is px of x. Similarly, y, it is py of y. Now conditional probability mass function p of y given x is the notation, is defined as joint divided by, so if you are conditioning on x, then it will be divided by px of x. It's a definition, there is no proof for it, it's a definition, you have to take it. P of x given y joint divided by y. Similarly, if you have continuous case, then you can have, suppose you are given joint PDF. This is your joint PDF, and you are given marginal PDF of x. And now I ask question, what is the conditional probability density function y given x? So it will be joint divided by, divide with what we should divide? You have to see on what random variable is conditioned, just to remember it. Okay, similarly f x given y divided by fy of y. Now similarly, if you are given a joint CDF, okay, that is capital Fxy of xy, and you are given the marginal CDFs fx of x, fy of y, you can define conditional CDF. That is f y given x is f xy fx of x, fx given y is fxy fy of y. And here is now the notion of independence. Independence means if occurrence of one random variable has no effect on the occurrence of other random variable. So that simply means if you have probability, suppose y is equal to some value y given x is equal to x. I am taking the example of discrete here. Now occurrence of this x has no effect, no influence on occurrence of y, so this probability will be equal to then probability y is equal to y irrespective of x's ignorant. Okay, so then we say that x and y are independent of each other. So here are equivalent definitions. So definition 1, suppose if conditional CDF fx fy given x is same as fy of y. Okay, so for discrete in particular, if conditional PMF is same as y given x is same as probability of y. In case of continuous, if f y given x is same as fy of y. Okay, one more definition we can get from this. So you recall that conditional, suppose CDF, how was it defined? Joint CDF, right? So in other words, joint CDF or PMF or PDF, whatever, can be written as conditional CDF times marginal. So if you are conditioning with respect to x, it will be multiplied with the marginal of x. If you are conditioning with respect to y, it will be multiplied with marginal of y. And now you see another notion of independence is that x and y are independent. In fact, it is if and only if fxy is simply product of marginals. Why? Because you take this particular term, okay, it is f of y given x, but if x and y are independent, you know that then conditioning on x has no effect on it, so we can remove that. So hence it becomes fx of x, fy of y. Similarly, if it is continuous, so joint PDF, if it factors as product of individual PDFs, we say they are independent. Similarly, if it is discrete, then we say that x and y are independent if joint PMF factors as product of marginal PMFs. Okay, so this is for continuous and this one is for discrete and this is for both. Okay, so I will end my lecture here at this point, and then we will continue with some other important concepts in next lecture. Thank you.